All right, good afternoon, good morning, good evening, good night, depending on when you're watching this video. If you're watching it on Monday, happy Thanksgiving. We are going to work through exercise number 4, which is given on slide number 19 of lecture set 6. So in this example, we are going to be working with the properties of the sampling distribution of the sample mean. So we're going to be computing the parameters of the sampling distribution of the sample mean for various sample sizes. And we are going to be utilizing the fact that the variable we are studying is normally distributed to establish or to describe the sampling distribution of the sample mean with more detail than just giving the parameters. So first off, what are we working with in this illustration? The question says the substrate concentrations in milligram per centimeter cubed of influent to a reactor are normally distributed with mu equals 0.3 and sigma 0.06. So we are measuring the substrate concentrations of influent to a reactor. Okay, so the variable here are these substrate concentrations. Or sorry, rather is the substrate concentration. And so that's the thing that we're measuring. Now, we are told in the problem that substrate concentrations are normally distributed. Okay, so if we say let X represent substrate concentration, then X is normal with mu equals 0.3 and sigma equals 0.06. Okay, so our variable are the substrate concentrations. We're going to define substrate concentrations to be X, but we could call it anything we want. And we know that X, the substrate concentrations, are normal, right? So they follow a bell curve shape. They have a mean of 0.3 and they have a standard deviation of 0.6. Okay, in part A, it says to us, or it asks, for all samples of size 50, give the 3 properties of the empirical rule with illustration. Explain why we can do this. Okay, so first off, part A, not B. Part A. Right. The variable of interest is normal. That means the sampling distribution of the sample mean is also normal. Okay. So variable of interest is normal. Therefore, sampling distribution of sample mean is also normal. All right. We can write out the parameters of the sampling distribution of the sample mean because we know what those are. Okay, so parameters of sampling distribution of sample mean are mu x bar equals mu, which is 0.3, and sigma x bar is equal to sigma over the square root of n, which is 0.06 divided by the square root of 50. Okay. which is 0.008. Actually, 0.0085. 0.009. Ugh. Okay, there we go. So we have our parameters. All right, so now what we want to do is construct the empirical rule for this sampling distribution. All right, so remember from the empirical rule, 68% is between mu plus or minus sigma. So in our case, it's going to be between mu x bar plus or minus sigma x bar, because our sampling distribution is normal. Okay. 95% is between mu x bar plus or minus 2 times sigma x bar, and 99.7% is between mu x bar plus or minus 3 sigma x bar. So those are the three properties of the empirical rule. 68% of the information under the bell curve is between 1 standard deviation of the mean. 95% of the information under the bell curve is within 2 standard deviations of the mean. And 99.7% is within 3. Okay, so we can illustrate this by sketching out a bell curve to represent the sampling distribution. So let's say that we have something that looks like this. Okay. And then on top, I have an illustration of the bell curve. Try and make that as symmetric as possible. Okay, one more time. It's hard to get it exact. All right, so that's supposed to be a symmetric bell curve. Just this last part here looks like junk. All right, something like this. So along the x-axis, we're going to have values of x bar. Okay, at the middle, we're going to have 0.3. If we move 1 standard deviation away from the mean, we're going to subtract off and add 0.09. Okay, so for example, if we were to go here and here, that's going to be 0.291 and 0.309. 1 standard deviation from the mean. And that means that underneath the curve, we're going to have 0.68 between those 2 points. Okay. Now, if I move 2 standard deviations from the mean, right, I'm going to move 2 standard deviations over now. So I'll have 0.318 here, and I will have 0.282 here. So then if I mark these with a red dash, that's going to be the 0.95. All right, and then if I move 3 standard deviations from the mean, so I'll just sketch those kind of over here somewhere. Okay, kind of on the tail edge. So that's going to be 0.273 on the lower end. Okay. And 0.327 on the upper end. All right, and then between those 2 points, so I'll use the blue lines here to mark that. That's going to be the 0.997. All right, so this is a rough illustration of the sampling distribution of the sample mean. Obviously, I should have given myself a little bit more space on the axes here, given the decimal points, but hopefully that's idea is clear. So what I'm doing here is I'm simply applying the empirical rule. So the empirical rule again states that between one standard deviation of the mean, you have 68% of the information. Between two standard deviations of the mean, you have 95%. And between three standard deviations of the mean, you have 99.7. And because the variable, so x, is normally distributed, that means that the sampling distribution of the sample mean is also normally distributed. So as a result, we can apply the empirical rule to the sampling distribution of the sample mean in this illustration because we know that it's normal since the population is normal. Now we can also do things like transform these into standard normal problems to find areas under the curve. Again, we can do this because we're working with a normal distribution. So part B, for example, what is the probability that X bar is less than 0.29 milligrams per centimeter cubed for all samples with n equals 5? All right, so here, first off, what are we looking for? Well, if we sketch a normal curve again, okay, and then these values here are going to be the X bar values. So this value here is mu X bar, which is equal to 0.3. All right, we're asking, what is the probability that X bar is less than 0.29? So if we mark down roughly where 0.29 is, we block this off, we're looking for this here. So the question that we're actually asking here is, what is the probability that X bar is less than 0.29? From our study of the normal distribution, we know that when we are asking about probabilities for normal random variables, our first step is to standardize to turn that random variable into a z-score. So for example, here, what's going to happen is, okay, we know z is equal to x minus mu over sigma. So now we can write z is equal to x bar minus its mean over its standard deviation. Okay, so z is equal to x bar minus mu, because mu of x bar is equal to mu divided by sigma over the square root of n, because sigma x bar is sigma over the square root of n. Okay, so we have z is equal to x bar minus 0.3 divided by 0.06 over the square root of 5 in this case, because this question is asking us the probability the mean substrate concentration is less than 0.29 when n equals 5. Okay. All right, so x bar here is 0.29. Okay, so that means that z in this problem is now negative 0.37. So this probability here becomes the probability that z is less than negative 0.37. We have a z-score now, so we go to our standard normal table. Okay, so we have negative 0.37. So that's negative 0.3 over to 7, come down and intersect them. That's 0.3557. All right, so the probability that x bar is less than 0.29 is equal to 0.3557. And we can say, therefore, the probability that the mean substrate concentration is less than 0.29 milligram per centimeter cubed for samples of size 5 is 35.57%. Right? So because the variable that we are studying, the substrate concentrations, are normal, that means that all sampling distributions, regardless of sample size, are normal. So in this problem, exercise B, we are told that, or we are studying sampling distributions when n equals 5. And we're asked, what is the probability x bar is less than 0.29? So we take x bar and we standardize it. We know that the z-score is x minus mu over sigma. So therefore, if x is now x bar, the z-score becomes x bar minus its mean, mu subscript x bar, divided by its standard deviation, sigma subscript x bar, which happens to work out to be x bar minus mu, because mu x bar equals mu, over sigma divided by the square root of n, because sigma x bar equals sigma over the square root of n. We plug in each of those terms because we know them, and we end up with a z-score. And once we have the z-score, we're applying exactly what we learned from lecture set 5, which was finding probability under a standard normal curve. Okay, let's look at a more sophisticated example, but it's the same idea. Determine the percentage of all samples of size 15 that have mean substrate concentration within 0.01 milligram per centimeter cubed. Okay, so what does this actually mean? Well, if we take our illustration of the normal curve, okay, so here, we mark down the center again. So this is mu x bar. Okay, so that's the 0.3 from above. I'll actually just write 0.3 because it'll make it a little bit more digestible. This question is asking us what proportion of the area under the curve is within 0.01 of the mean. Okay, so that means if we were to just sketch down 2 points, so this is 0.3 plus 0.01, and this is 0.3 minus 0.01. What we want is this whole chunk right here. Okay, so that's what we're looking for. So in terms of a probability statement, we can start by saying, what is the probability that mu x bar minus 0.01 is less than x bar is less than mu x bar plus 0.01. So that's what it means to be within 0.01 units of the population mean, or of the mean of the sampling, or of the mean of x bar. But we know what all of these different quantities are. So we know what mu x bar is. So this thing reduces to the probability that mu minus 0.1 is less than x bar is less than mu plus 0.01. This reduces to the probability 0.3 minus 0.1 is less than x bar is less than mu plus 0.01. So now we have the probability 0.29 is less than x bar is less than 0.31. So this is a much more digestible statement than the original statement. We're just asking, what is the probability x bar is between 0.29 and 0.31? So we have to standardize our two values, and then we can just look up the areas under the curve, and we can solve. So this is the probability x bar is less than 0.31 minus the probability x bar is less than 0.29. Okay. All right, so we need to standardize. I'm going to just do that over here. Okay, so standardize. So we know Z is x bar minus mu over sigma divided by the square root of n. Okay, so whenever we're standardizing x bar, our z-score formula just changes to accommodate the parameters of the sampling distribution. So in the lower limit case, this is 0.29. We'll call it Z1 is 0.29 minus 0.3 divided by 0.06 over the square root of 15, because in this example, we're asking for samples of size 15. So this is negative 0.65. Okay, and then Z2 is going to be 0.31 minus 0.3 over 0.06 divided by the square root of 15, which is 0.06. So then we have the probability Z is less than 0.65 minus the probability Z is less than negative 0.65. Okay, so if we go to our normal table, we look up 0.65, 0.605, which is 0.7422. Okay, and then we look up negative 0.65. Okay, so negative 0.605, which is 0.5278. Right, so we have 0.7422 minus 0.2578. Okay, which is equal to 0.4844. Right. So then in this case, we could say something like the proportion or the percentage of all samples of size 15 that have mean substrate concentration within 0.01 milligrams is equal to 48.44%. Okay, so as always, if you have any questions, please let me know.